Our paper reports experiments on the search for Bose-Einstein condensation of excitons in the semiconductor cuprous oxide. This system has been studied for a number of years, but a controversial issue remains. Here's the discovery of Bose-Einstein condensation in a gas of atoms. At 170 nanokelvin, atoms dropped into the lowest momentum state. In a photoexcited semiconductor, the role of an atom is the exciton, a bound electron-hole pair. Could a gas of excitons undergo Bose condensation? Here's the experiment. The crystal is cooled to 2 degrees Kelvin and excited by a laser, creating excitons which diffuse from the surface. The electron and hole in an exciton recombine, emitting a red photon. At low excitation levels, the spectrum exhibits a classical distribution of energies at the crystal temperature. Here's an image of our 2 millimeter crystal with a green laser beam exciting the surface. The expanded view shows the cloud of excitons diffusing into the crystal. The size of the cloud depends on the lifetime and mobility of an exciton. Our experiments time resolve both the total number of excitons and the gas volume in order to measure the density of the gas versus time. Unfortunately, as the gas density is increased, the exciton lifetimes decrease, limiting the density to well below that for Bose condensation. This density-dependent lifetime has been attributed to Auger recombination. 2 excitons collide and 1 recombines, giving large kinetic energies to the remaining electron and hole, which eventually thermalize into a single exciton. The decay time of luminescence gives the Auger constant A as a function of temperature. Theoretically, the Auger constant increases with rising gas temperature, and early experiments seem to support this. However, time-resolved measurements of exciton density show an inverse temperature dependence for A, and it's 4 orders of magnitude larger than predicted by Auger theory. Our proposed answer to this puzzle is the binding of excitons into biexcitons. The inverse temperature dependence of the exciton decay rate is consistent with the formation of excitonic molecules, like 2 hydrogen atoms forming an H2 molecule. Biexcitons dominate at low temperature and have a very rapid Auger decay. In effect, the exciton Auger constant is replaced by the biexciton capture coefficient, which is inversely proportional to gas temperature and explains the exciton lifetime data. Consider a gas of excitons trapped in a potential well, produced by stressing the crystal with a rounded glass plunger. Excitons created at the crystal's surface are drawn into the potential well, where the stress is highest, and the semiconductor band gap is lowest, producing an effective trap for the excitons. Measured here is the luminescent spectrum of strain-confined excitons, showing both ortho and para-exciton luminescence assisted by phonons. The decay of exciton luminescence after direct excitation of the strain well is explained by the formation of biexcitons. The capture coefficient C agrees with that measured for the unstressed crystal. The final slide is a brief summary of conclusions and perspectives.